Objective of today's experiment is to study and obtain waveforms for following modulation schemes: pulse amplitude modulation, pulse width modulation and pulse position modulation. As well as today we are going to perform the demodulation part also. These two are two different experiments. So objective of the next experiment is to study and obtain waveforms for the demodulation of pulse amplitude modulation, pulse width modulation and pulse position modulation. Today we are going to use the apparatus, the kit. This is for PAM, PPM and PWM modulation and demodulation trainer ST2110. This is a kit where we can perform. There are the blocks for amplitude modulation, position modulation and width modulation, as well as we have a low pass filter that we are going to use it as a demodulation. And we will see how the modulated output looks like and how after demodulation we are retrieving the message signal back. In pulse modulation systems, we use pulse signal as a carrier signal, as in AM modulation or FM modulation, any analog modulation, because pulse modulation is also an analog modulation in which the carrier is pulsating nature, or pulse signal is used as a carrier signal. We have a message signal that is a continuous signal, analog signal. So here we have this block for pulse output. This is for carrier generation. We have 4 options: 8 kHz, 16 kHz, as well as 32 kHz and 64 kHz. So we have 4 options for carrier. Whatever be the frequency we are going to use, we will see in some time. And there is a function generator here for message signal. As I always tell all of you that this is a prototype kit where we need to generate the message also and carrier signal also. In real scenario, there is a message signal, the speech or data or information is there. In whenever we are performing on a prototype kit, then we need to generate message signal also. Unfortunately, this block is not functioning properly, so we are going to use another function generator to take the modulating signal or input signal. So here we have this function generator where we are going to generate function, a sinusoidal function. This is a sinusoidal function with a frequency of 1 kHz. So here we are using 1 kHz of frequency, 1 kHz frequency signal as a message signal. So we will see how this signal looks like, and that particular modulating signal, the single tone frequency signal, we are going to take here as an input. And after demodulation, we will see we are retrieving this 1 kHz sinusoidal signal or not. So this is our message signal, 1 kHz sinusoidal signal. So this is the probe for this function generator. We have taken this output using the probe. We will use DSO in order to display all the waves, the carrier signal, the message signal, as well as the modulated output and the demodulated output. So when we talk about amplitude modulation or analog signal, analog modulation, there are 2 types of analog modulation: continuous wave modulation as well as the pulse modulation. Pulse modulation is also a type of continuous wave modulation. In AM or in FM, we used to send whole information. The signal is varying from minus AM to plus AM, the whole peak value, as well as the frequency. Everything is getting incorporated in carrier signal and it is getting transmitted. If we are going to sample the message signal and send those sampled values only, so if that can be done using a pulse carrier signal. If you are multiplying a signal, continuous time analog sinusoidal signal with a pulse signal, then the samples will be taken. That is the pulse amplitude modulation. We will see. So what I am trying to say here is, if we are not sending the whole signal, the message signal, but we are taking sufficient samples of the message signal and send it using modulation and then transmit it, then that particular thing is called the pulse modulation. So in pulse modulation, we are taking samples of the message signal, and those samples are the values or information that we are sending. In other modulation schemes, analog modulation schemes like amplitude, DSB, SSB or FM or PM, we used to transmit the whole information, the signal value at each instant. And in pulse modulation, we used to send the sampled value the sufficient sample so that it can be retrieved, and there is no distortion at the receiver end after demodulation, because we are taking sufficient samples so that we can demodulate it completely. So what is difference between the DSB SSB signals or a pulse modulation signal is only that in DSB AM or FM modulation we are sending the whole information or the value of the signal at each instant, and in pulse modulation we are taking samples and we are sending it to the through the transmitter to the receiver. So here we are taking samples and sample values are getting transmitted, but there are pulse code modulation as well as delta modulation. These are the digital format of pulse modulation. Pulse modulation can be categorized in two formats, analog as well as digital. In analog we have PAM, PPM and PWM, and in digital thing we have PCM, pulse code modulation. What is difference between these two? If we are taking samples and sending samples in pulse amplitude or pulse position or pulse width modulation, then the amplitude can be anything, any real value it can be. But when we are categorizing it into quantized levels, and we are sending only the amplitudes lying on those quantized levels that are getting encoded, as you have learnt in PCM TDM systems, that in PCM that one is a digital modulation scheme, it is also a pulse modulation technique, but it is a digital format. So in that case the amplitude is quantized actually, and quantized level of amplitude is getting sent. But in these cases, the pulse amplitude and pulse position and pulse width modulation, we are sending the sampled values, but the intensity or amplitude level of the message signal can be any, it can be any real value. But in case of pulse digital modulation or PCM or delta modulation or differential PCM or adaptive delta modulation, all these schemes are digital format of pulse modulation. So in all these cases, the digital format, we are going to have quantized levels, and the amplitude or information only lying on that quantized level are going to encode it and send. So I hope you have a basic idea about this pulse modulation, why it is different than the normal or standard continuous modulation. It is also analog modulation. So what I am going to show you this signal. First I am trying to show you the message signal. This is the signal, and I am going to show you this message signal. I have recorded this message signal on our DOC. You can see it. This is our message signal. This is our message signal. This is our message signal, sinusoidal continuous time analog signal. This is of 1 kilohertz frequency, and this one yellow the other channel I have used. I just tried to illustrate the carrier signal. This is the carrier signal. And at that time I took 8 kilohertz, so it is 8 kilohertz carrier signal, pulse signal. So in pulse modulation we are having the information in this modulating signal or message signal, and this is our carrier signal, that is pulse signal. So we have all these three equipment that we are going to use. This is the kit for this, and the function generator, because this particular block is not working properly, that's why we are going to use this, and the other thing is our connecting probes. So we are going to do the connections. So first of all, let me show you this message signal once. So I am going to use any of the channel. I am going to use this one just to show you how our message signal looks. This is ground common. I am making this common as well as connecting it to one of the ground, because this is the ground. This is ground, so I have connected this wire so that wherever we will need this, I will use that. So I am connecting this to the ground. So I have connected the black probe of this function generator as well as the black probe of one of the channel of DSO, and make them ground. And the second thing, I am going to connect the red one to the live of the DSO, so that now it was stopped at a stop condition. I am going to run it. You can see this is at a stop condition, so I am going to run it. If I will run it, it will turn green since it is red. You can see this is the running wave, our message signal of 1 kilohertz, If I stop it, then you can see it, since it is continuously running in dynamic mode, so you can't see it clearly, but it is a sinusoidal wave. Let me stop it. I'll stop it, then you can see this is the message signal that we are giving here for all the cases, for amplitude modulation or pulse width modulation or pulse position modulation. In all the cases we are going to use this thing. This is our message signal. So this is just for your illustration, and I'm going to show you also the carrier signal, so that you can get clarity that what is the carrier signal we are using. So I'm going to show this carrier signal also. This is a pulse output, and I am taking 8 kilohertz one, so that we can change it. We will change it during our practical, so that we'll see. Now I am making one of the terminal as ground. This one is the ground. I am using the same channel, the second channel, the green one, for this. So I am just taking the output. I need to run it, because I am going to run the output, so that you will see there is a pulse output. If I will adjust the CRO in such a way, if I will stop it, then you can easily see it is a pulse nature signal. It is a pulse signal. This is the signal that we are going to use it as a carrier here. So we have a message signal of sinusoidal nature, and we have a carrier signal of pulsating nature. This is all about the pulse modulation. In pulse modulation we use pulse signal as a carrier signal. So I am going to give the input. We are having the input from the function generator. So I am going to give the input to this modulating signal input. This is a modulation signal input. This is our message signal. So I'll connecting wire here, and I'll give the sinusoidal signal here, the message signal, and I need to connect a ground. So I'll connect a ground here. This is the ground. So I'm connecting this ground. Yes, and I'll show you. And this is our pulse input. This is our pulse input. So this is a carrier, and this is a modulating signal. And if they both get multiplied, if you multiply both of them, then you will see the continuous time signal will get sampled for the width of this pulse. So this particular thing we will see, and the output that after sampling we are going to get is pulse amplitude modulation. Pulse amplitude modulation is simply sampled output, or if I'll show you this one, and sometime this one is a sampled output, and there is a flat top output. I doubt if this particular pin is not working fine, but sampled output when I show, then whatever be the natural sampling, this will give the result of natural sampling to us. So I'm going to show you the output. I'll run this so that you will see the output. This is our sampled output. When I'll stop it, you will able to see this is our sampled output. I need to stop it so that you will see. This is the, let's see, this was our message signal, a sinusoidal signal, and it is getting sampled at the rate of 8 kilohertz of our pulse signal, because pulse signal is of 8 kilohertz. So we have sampled this, and this is the sampled output. This is a pulse amplitude modulated output. This is our PAM signal. This is pulse amplitude modulated signal when we are using natural sampling. Natural sampling means whatever be the amplitude here at this point, this will be maintained like that. The nature of the wave, you can see the nature of the wave, it looks like a sinusoidal, but if we are going for flat top sampling, then this top will get flattened. So I'll try once, because I doubt this pin is not working fine, but what you will see, whatever be the voltage over here, it will be constant. The top will be flattened. I'll see, I'll try once if it's working fine. Actually it's not. So you can see this is our natural sampling or pulse amplitude modulated output. So you can say this is our pulse amplitude modulated output. This is our modulated signal, right? So what I'm going to do is I'm going to demodulate it so that we can complete at least one part of this at once. So we have seen the pulse amplitude modulated signal, so I'm going to demodulate it using a low pass filter. So I'm connecting this sampled output to this input of the low pass filter, and the output of low pass filter is going to give us the same modulating signal or the message signal that we were getting here, or we have given as an input. So we can say then we can say the our modulated signal is getting demodulated. So I'll check the output here or at this pin, and we will see we are getting the same sinusoidal signal or not. So you can see we are getting the sinusoidal signal here. We are getting the sinusoidal signal here, the demodulated output. If I'll stop it, then you can see this is our demodulated output. So whatever be the input we were giving at the input part, our modulating signal, we are retrieving it back. So we have illustrated the pulse amplitude modulation, the modulated output you saw, and this is the demodulated output. This is our message signal. So pulse amplitude modulation is just a sampled output. Either you go for natural sampling or you go for flat top sampling. So that was our pulse amplitude modulated signal, and this is our demodulated signal. So we can say that whatever the information we were trying to send, we have retrieved it back at the demodulation part or receiver part. In real scenario, we have a transmitting antenna where we transmit that signal, and there is receiver at a far place that receives the signal and demodulate it and get whatever information the transmitter or the person who want to communicate at transmitter end was trying to send can be received and demodulated in a similar way. So this is a prototype kit. So we have illustrated this, that we are giving an sinusoidal signal as a message signal having some information of 1 kHz signal, and we are modulating it using a pulse amplitude modulation, and we transmitted it and received it at the receiver part and demodulated it and retrieved the same message signal. So we are done with the pulse amplitude modulation and demodulation. So now I am going to illustrate the pulse position modulation. So here is the block for pulse position modulation. You can see this is the block for pulse position modulation. This is the block for pulse position modulation. So we are going to give the modulating signal input here at the pulse, this block. We are giving modulating signal input here, and we are going to see the modulated output of this ppm output. Now I'll see the pulse amplitude modulated signal, the pulse position modulated signal here. When I'll stop it, you will come to know, you will come to see how the signal is look like. This is the pulse position modulation signal. As per the instantaneous or sampled output of the signal, the position of the pulse are getting shifted. The carrier signal in pulse position modulation, you must notice that the amplitude and frequency or amplitude or time period of the carrier signal is not going to change. Only position of the signal is going to get changed. So wherever the instantaneous value is higher, the position will be higher. More waves will be closer, or when it will be low, the waves will be farther. So it is in some way we are changing the position of pulse signal, and that particular thing contains our information of the message signal. So this is our ppm signal or pulse position modulated signal. This is how our ppm signal looks like. If I'll little bit widen it, then you will see the position of the pulses are changed as per the sampled value of the instantaneous signal. Our message signal is same, that 1 kHz of sinusoidal signal, and our carrier signal is also same 8 kHz as well as and we saw this is the pulse position modulation system. So what is next thing, we are going to demodulate this and see how we are retrieving the information or signal that we have transmitted. So again again I'm connecting this ppm output to input of the low pass filter. This is a demodulation circuit. We are just connecting it to the low pass filters, and we will retrieve the modulating signal here. So what was our modulating signal? A sinusoidal signal of 1 kilohertz. So here also we are getting the same, because I am taking the output here. Once I'll stop it, then you will come to see this is our message signal. So we have modulated using ppm scheme the pulse position modulation, because position of the pulse signal or carrier signal is getting changed as per instantaneous value of the message signal, and we have retrieved the message signal back here. So this is our message signal after demodulation. So we have demodulated the signal. So we have performed the pulse position modulation. You saw the pulse position modulated wave, as well as this is the wave after retrieving the information back. So we have retrieved the information back, or we can say we have performed demodulation of the pulse position modulation. So our next scheme in this experiment is pulse width modulation, where we can say pulse width modulation or pulse duration modulation. There is different name for this, but we are going to see how the modulated wave after pulse width modulation looks. Our message signal is same, so we are going to give here pulse input. So I am going to give pulse input here. I am going to give the pulse input here. So I have given the pulse input 8 kilohertz. We will change this 8 kilohertz to 16 and 32 and 64, and we will see what changes we are getting in this case. And the second thing I need to apply is modulation signal input or modulating signal or our data. So I am applying here the data from the function generator. This is our data. So here we will get PWM output. So I am going to see how our PWM output look like. I am going to see on the DSO. So I am going to see output at the pin number 10. We will get the PWM output. So you can see easily, if I'll stop, then you will come to know this is our PWM output. In PWM case, you will see in 8 kilohertz it is not very much visible that we are performing PWM. Let me change the pulse output, the carrier signal frequency. Let me change to it to 16 kilohertz, or let it be 32 kilohertz, and see how we are getting our pulse, this output. In pulse width modulation, the duration of the signal or pulse signal is more for higher amplitude of the message signal, and the amplitude of the pulse signal or a duration of the pulse signal is less for lower peak or the negative peak. So at the negative peak there will be like zero duration, or you can say there won't be any pulse. So here you can see, if I'll stop it, then you will see at some places there are no pulses. This is the negative peak of our message signal or sinusoidal signal. When there was a negative peak, then this duration is, there is no duration. If I'll expand it little bit, then you will see these signals are also of not equal duration. Where the amplitude is less, the duration is less. Where amplitude is more, duration is more. So this is our pulse width modulation or pulse duration modulation, in which the modulation scheme we are having the width or duration of the signal as per instantaneous value of the message signal. So here we can say this is our pulse width modulated signal. This is our pulse width modulated signal. After demodulation, we will see how we are getting the output, or we are retrieving the input again. So I am going to connect this PWM output to the input of the low pass filter. Here I am connecting this, and we will see on the DSO after demodulation how we are demodulating the signal. you can see here we have retrieved the message signal back after PWM modulation. The modulated wave, PWM modulated wave, is getting demodulated. I'll stop it, then you can see it clearly. This is our sinusoidal signal of 1 kHz that we have transmitted. So whatever information was there in this signal, we have retrieved it back. So at receiver part, the receiver will come to know what information was sent from the transmitter. So we have illustrated here the pulse modulation schemes, the amplitude modulation as well as position modulation and width modulation, how the modulated wave look like, and how after demodulation we are going to retrieve the message signal. So here also we have continuous time or analog nature of message signal. We have a continuous time sinusoidal signal as a message signal. So what is difference, as I told earlier also, that we are not sending each and every value or each and every information at every instant of the signal, but we are taking samples at regular interval, and we are sending that much information, and those samples must be sufficient so that that can be retrieved at the receiver thing. And when I am saying sufficiency, it means they must conform with the Nyquist criteria at least, so that we can have the process, so that we can retrieve the whole signal back, and there must not be any distortion at the demodulation part. Okay, so we have a continuous time signal and we have a pulse nature of this carrier signal. So this scheme is also a continuous time modulation scheme or continuous modulation or analog modulation scheme, in which the carrier is of pulsating nature or pulse signal, and we have options here on at our kit to use 8, 10, 16 or 32 or 64, any of this carrier signal. So we have generated the carrier signal from here. We could have generated the message signal from here because we have the knob to adjust the frequency of the message signal, but this particular pins are not working fine. There must be some error in the circuitry. So we have used this function generator. This is a function generator, and we have generated frequency of sinusoidal nature of 1 kHz, and we have used this particular signal as an input. So our message signal is this. We have seen the output after modulation using amplitude modulation. So in amplitude modulation, it is just a sampled output. Whatever sample, and in sampling, if you multiply a sinusoidal or analog nature signal, mathematically also you can see that if you multiply modulation input, this sinusoidal of 1 kHz with a frequency of 8 kHz pulsating signal, then it will get sampled. You saw the output of pulse amplitude modulation when we are performing the amplitude modulation scheme. So it can be sampled, natural sampling. The output that we saw is of natural sampling. We can have the flat top sampling also. This particular pin is not working fine because there might be some error in the internal circuitry. Otherwise I could have shown you the flat top sampling also. Whatever the sampled output we were getting, the top will get flattened in flat top output, and that particular signal, this one and this one, both you can say as pulse amplitude modulation, because whatever the information is in modulation signal input or modulating signal or our data or information signal, that is getting sampled by this pulse input. So in pulse schemes or pulse modulation schemes, we are not transmitting the whole information, but we are transmitting the sampled information. Whatever be the information that is getting sampled, that much information is getting sent using pulse modulation schemes. So amplitude can be any. Amplitude can be of any value, any real value. Then this is called pulse amplitude modulation or pulse position modulation or width modulation, or we can say this is a analog modulation scheme or continuous time modulation scheme using pulse signal or pulse modulation. When we are having quantized labels of amplitude also, we have quantized level of amplitude, means there is a peak of -5 to 5 volt of sinusoidal signal, message signal, but you have quantized it in 4 levels and encoded it in form of 000111011. In that case, whatever amplitude you are going to send is one of the quantized level you are having. So those schemes are called pulse digital modulation schemes, and the examples can be pulse code modulation or differential PCM or delta modulation, we have already performed the PCM TDM system experiment in our previous experiment. So we saw that pulse code modulation, how we quantize the labels and how we send the encoded output. We saw the analog to digital modulation, analog to digital conversion there also, and PCM output. So you can easily see that this is a analog or continuous time modulation using pulse modulation, and in digital scheme of that pulse, we have PCM, DPCM, or delta modulation or adaptive delta modulation. So in amplitude modulation, we have the sampled output. In pulse position modulation, position of the pulse is getting shifted or changed as per the instantaneous value of the message signal. In pulse width modulation, duration of the signal or the carrier signal is getting changed as per the instantaneous value of the message signal. So whatever with the instantaneous or sampled output of the message signal we are having, accordingly the amplitude or position or width of the pulse signal is getting changed. So we can say we have performed the amplitude modulation, position modulation, and width modulation, and in each case we have used this low pass filter as a demodulation circuit. We just taken output using a wired mode. As I told you, in real scenario we have transmitting antenna and receiving antenna. Transmitting antenna transmits the modulated output in the environment, and at the receiving end, receiving antenna receives it. But since we are performing it on the kit, and it is a prototype where we are trying to illustrate the concept and basic methodology behind this scheme, so we have connected directly using wired mode. So whatever we are assuming that whatever output we are having at the transmitter end, we are getting the same input at the receiver end. So we have connected using it in a wired mode. So we have this circuit for PAM, PWM, and PPM. So we have performed both the experiment, the pulse amplitude modulation, pulse position modulation, pulse width modulation, and the second one in which we have performed demodulation of all these schemes. You saw the carrier signal, message signal, as well as the modulated output and demodulated output also. So we have performed the whole experiment. When you are going to prepare the report, then you need to prepare report separately for both the modulation part and demodulation part. In first report, you are going to include all the modulation schemes of pulse, the pulse amplitude modulation, position modulation, width modulation, and you need to show how the what were our message signal, what were our carrier signal, and what we have obtained after modulation. This in all three cases you need to include these informations: carrier, message, as well as the modulated output. And in when you are preparing for demodulation or the next experiment, then you need to include all the information, and you need to show that we have retrieved the message signal back, and we are getting the same message signal as we are sending from the our transmitter part. So at demodulation, you need to show the modulated output as well as demodulated output, and you also need to mention about the carrier and message signal. So this is our experiment. This experiment includes two of the experiment as mentioned in your curriculum. First one is for modulation and second one is for demodulation. I hope that's clear. Thank you.